Welcome back to RISC-V assembly language. We have learned 8 RISC-V assembly instructions so far. In the next 15 minutes we are almost going to double that number. The instructions that we have learned so far deal with addition and subtraction operations with the memory. We can actually build a computer with that. That would be more like a calculator or a stack machine. We could build a stack machine. Those kind of things were popular, say in the 60s or 70s, and all the action there happens on the stack. But in order to support modern programming languages, we need to support computer decision making. Example of that in C is the if statement. And in RISC-V there is no if statement, but there is its counterpart. I wouldn't say it's an equivalent, it's a counterpart. That is a set of branch instructions. Branch instructions are those that support decision making. They change the order of executions of instructions in the code. So here is an example of one of those instructions, branch if equal. Mnemonic is BEQ, and it compares the contents of the registers reg1 and reg2, and if they are the same, if they are equal, then it will jump to a label L1. Label L1 is just a symbolic address for another part of the code. Otherwise, if the contents are not the same, it will execute the next statement, next instruction that is in our program, next line that is in our program. BEQ has its counterpart, BNE, which stands for branch if not equal. It will take a look at the contents of two registers, and if they're not equal, it will branch. There are two types of branches in assembly, and RISC-V is no different than that. There are conditional branches and unconditional branches. Conditional branches basically evaluate something that we ask them to. Examples, what we have seen, are already branch if equal and branch if not equal, but we can also compare magnitude. So we have two instructions, branch if less than, and which is BLT, and branch if greater than or equal, which is BGE. And then we have unsigned versions of those, BLTU and BGEU. There is an unconditional branch, which in RISC-V is a jump. It is just encoded as J and then a label. Whenever we run into that instruction, we basically jump to another location in a program. It's like a go-to. It is always executed. It corresponds to an always statement. Now, when somebody may ask, oh, can we just make an unconditional branch out of a conditional one? For example, we say branch if equal x0 label. Yeah, and that will definitely always jump to a label. But there is one subtlety there. The range of that branch, the range of branches, is shorter because we are limited to 32-bit instructions in RISC-V. So these 32-bit instructions, you have to encode somehow the type of the instruction, which kind of registers are we comparing, which ones of the 32 registers are we comparing, and then there is a little bit to place the label, which is essentially an immediate value. In jump, we just say jump and then have some kind of an immediate value. So the range of an unconditional jump is longer, reaches farther. Let's take a look at a couple of examples of how does an if statement translate to RISC-V. So here is a piece of C code. If I equal j, compares the values of I and j, then we should say that f equals to g plus h. Let's see how does that translate into RISC-V assembly. The first thing, we need to figure out if I and j are the same and their contents are in the registers x13 and x14. And look at this. Here is something that might surprise you, but totally makes sense. Instead of saying branch if equal x13, x14, we are using B and E. We are inverting this equal condition. Why are we doing that? It makes sense, because if you think about how does the flow of execution go here, this is what happens. If B and E branch if not equal, if these two, the contents of the registers are not equal, we'll go this way. If it is not true, we'll go down. So in this case, in the C instruction, we would like to add the two numbers if I and j are equal, which is essentially what happens automatically on the next instruction if the branch is not taken. So it does make sense in this case to flip this around and ask, oh, if they're not equal, then jump around this instruction that we would like to do if they are equal. So if they're not equal, we'll jump around or branch around, to be more precise, go to the exit. If they are equal, then the add will be executed. Hopefully this made sense. This is a very common thing that we'll do, and it is very helpful if you think about it this way: the direction of true and direction of false. Here is another example. It's an if-else statement, and it's exactly the same, except that we added the x condition here that will take f equals to g minus h if I is not equal to j. Now this one you can do in different ways and it'll look similar, but let's stick to the idea that we always flip this original condition. So we'll have b and e, and then if b and e is true, if x13 and x14 are not equal, we will skip to else. In else, we'll we'll subtract the two registers, and then we'll exit. If they are, if B and E does not branch, if this instruction doesn't branch, we'll execute the next one, so we'll add the F and J and H and store it in F. Now, there is a common mistake, and I've made it gazillion times, and that mistake is by omitting this J instruction to exit. What happens if we don't have it there? So then, if we don't branch here, we will add the contents of the two registers and put them in X10. Then, if there is no jump, we will execute the next instruction that will subtract the contents of two registers and put the result in X10. And you'll always do that. And you'll be looking at there, debugging this code and scratching your head. What, why do I never get this add to happen even though I wrote it in there? Well, because it gets overwritten. The content of a register gets overwritten. So this jump is a must. Just a quick words about the magnitude comparison RISC-V. We said we already have them. We have branch on less than. We also have branch on greater or equal. But we do not have a branch on less than or equal, and we do not have branch on greater than. Why? Because we are trying to reduce the number of these instructions, and those are absolutely not necessary. We get them by flipping the order of two operands, the contents of the two registers that we would like to compare. So they're absolutely not necessary. But what is necessary is to have an unsigned version of a branch. So there is a BLT-U and BG-EU that compare the unsigned versions of the integers. It's really important to remember which one are we using when. So whenever we are comparing signed numbers into its complement, we are using BLT, and if we would like to compare unsigned, it is a BLTU. Now, one thing that is kind of convenient to remember here, which instruction do we have? Do we have BLT in our instruction set or BGT? Well, the way how I remember it is by remembering that there does exist a type of a BLT sandwich, but I have not yet seen a BGT sandwich. BLT stands for bacon, lettuce, tomato. All right, let's move on and take a look at a little bit more complex control. So you'll find different types of loops in C, for example, while, do while, and for. They are mapped on exactly the same set of branching instructions that we have seen so far. No difference there. Let's take a look at a little bit more complex example here. So here is a piece of C code that looks at an array of 20 integers and adds them all up. So color coding here is used to easily identify what goes where, which registers correspond to which variables. So first, we'll take the pointer to the first element in the array A0 and copy it to register 8. Because we're going to be changing it and we do not want to destroy it. That's another good practice that we would like to use in the assembly. We don't want to destroy the content, the starting content of that, of that register, because we may need it later. Then we need to initialize everything. We'll initialize sum to 0, index I to 0. And we do need to store the final value 20 in the register X13, because we'll need to compare the I to that value and find out if we have completed our summation. Remember, we don't have branching with immediates in RISC-V. Contents of both variables that are going to be compared need to be in the register, so there is no comparison to an immediate. So let's start our loop. Here is the start of the loop, and there is one really important thing that I want everybody to remember. Test the condition if you should exit right away, because it's the same logic that we have been following so far. If the condition to exit the loop is true, we just go to the end, to done. So in this case, if X11, if I has reached 20, we just go to done, that's yes. If not, we stay inside the loop. So when we are in the loop, we load the next value of the next element of A into register X12. We add it to the running value of the sum, which is in X10. Then we increment the pointer. And remember, we would like to load the next integer. Integers are 4 bytes wide. RISC-V addresses every byte in the memory. So we need to increment this pointer by 4. This is a very common mistake. Always keep that in mind, because you are going to be having a fun time debugging these if you are not incrementing, if you're working with integers and not incrementing memory pointers by 4. We increment I by 1, and that's basically it. We jump back to the beginning of the loop. When we are just missing one more label, which is done, to say that we have exited this loop. And that's it. That wraps up our discussion of branches. See you in a bit.